Okay, so the next example is the one which we are going to look at the sums of squares of deviations about the mean. So we should show that the sum of xi minus x bar squared is just equal to the sum of xi squared minus twice x bar times xi plus x bar squared. So we know that if we have this, then it's easier to split these individual quantities on their own. So this becomes the summation of x squared, so which we have here. Now we know that 2 and x bar are constants, so we can factor them out when we are summing this over this quantity. So 2 and x bar, those are quantity, they are constant. So that's why here you see 2x bar outside of square of xi. Then plus the summation of x bar square. Again, if you see here, so this is by rule number 1 and 2. Rule number 1 is the one that we know that here we just expanded this square, but we know that when we have in brackets quantities, we can take the summation through each of those quantities. That's rule number 2. That's rule number 1, and number 2 is now the ones which we know how we can deal with constants. Now, and here we know this one is a constant, so summation of x bar square, it means we just have to multiply n to x bar square. So that's why we have here n x bar square. This one, if you recall the definition of the mean, then you know that this one also gives us n x bar. So this one gives n as n x bar. What means we're going to have x bar and n x bar. So 2x bars, that's why we have x bar square here and that the n there. And 2 is maintained here. So this is what we have on step number 3. So on step number 4, now we can add the like terms here. So we have minus 2 nx bar square plus nx bar square. Therefore, if we add these two, we should remain with minus nx bar square. And then in the beginning here, we have the summation of xi square. So when we reach here, we can do some manipulations. If you look at this quantity, what we have here is just this quantity here, summation of xi square, then minus, now you look what we have here. So what we're having here is that we know it's coming from the definition of x bar, from the definition of the mean. Basically, I can show you that we know the mean is just xi over n. Now, if you look here, you have x bar square. So it's like you have this. Now, what will this give you? This will give you summation of x bar on top over n squared. If you have to remove the brackets, that is what it will give you. So, but remember that we already have here, we have this n. So what this is only that the x bar square, which gives us the summation of x square over n square. But we have the n here, multiplying x bar square. So if we put it here, there, so remember there was the n is there, then this one is n square. So we cancel that and we remove that too. That's why you see that we only have one n down there. So this is another way that you can write this quantity as this one. Now this one does not have any means, so which means you can calculate the sums of squares of deviations about the mean, even though you are not given the mean, or you have not calculated the mean. You can still calculate the mean, the sums of deviations about the mean. Okay, next, I will take you to special quantities. So this summation of xi square is referred to as raw sum of squares. And this one here, the summation of xi minus x bar square, is referred to as corrected sum of squares. This may be obtained by subtracting the correction factor, this one. So we can also get that by subtracting the correction factor from the raw sums of squares. That is what we have just seen here. Thus, the corrected sum of squares is an alternative and more convenient name for sum of squares of deviations about the mean. So the sum of squares of deviations about the mean can also be referred to as the corrected sum of squares. Now let's look at the mean of grouped data. Now this one, remember we already saw this, but we are defining this formally using the sigma notation. If you have a set of n observations of a discrete variable r, which have been grouped according to the k distinct values that it is possible for r to take, this may be expressed in a frequency table as follows. So you have variable values, distinct variable values R1, R2, R3, up to Rk. And then the frequency, how many times R1 appears, that's F1. We have F2, F3, how many, this is how many R3 appears, and then Fk up to Fk. Here we have the total number of observations. Now n is the same as summing the independent frequencies here. That will give you the total number of observations. Now, the total of all observations is equal to summation fi times ri. That gives us the total of these observations. Now, fi, this is the frequency here, ri is the distinct number there. And we have already done this before when we are looking at means of group data. Even when we are looking at the data example, we already saw these this kind of relationships. So if we have that scenario, then the mean of group data of a set of discrete variable grouped so that the values ri ranging from, as I range from 1 up to k, occurs with frequency fi is given by this one. So R bar is the mean of group data, which is just the summation of the observation, the total of the observation there, which is summation of fi ri over n. If you see this, we surely have come across this one. We have done these examples that use this formula. And so, so the mean of group data for a continuous variable. The one before, which we have seen in the previous slides, was for a discrete variable. Here we are looking for a continuous variable. So for a continuous variable, you already remember that we group the data into class intervals. And so what is very important here is the calculation of class centers, because this is the class centers that we are going to use here. So if there are k intervals and the centers of these intervals are at xi, I from 1 to k, we may summarize the observations they grouped frequency table as follows. So we don't have class intervals. Maybe above there we should have class intervals. But what we have are the class centers, x1, x2, x3, up to xk. These are class centers. These are the frequencies, the number of observations falling in a particular class interval whose center is x1. Again, f2, likewise, up to fk. So if we have that, this is the formula for the mean of group data for a continuous variable. Now, you don't notice the difference here. The only difference is the replacement of Ri by Xi. So here we have X, there we had R, and there we had R bar, here we have X bar. So the formula is just, the way you do it is just the same, except that we have just replaced Xi here, and Xi here is the class center. So basically that's the difference. Where in that case, Ri was just a distinct observed value of a discrete variable. So assuming you have this, so this is now the definition of the mean from the sample. If you look from what we have been having, we have been having a big N, more or less, assuming that we have observed from a population, a set of observations from the entire population. But in most cases, when you are given a sample, the mean is normally defined by dividing an N down here and the numerator, the total. So if we have, for example, a sample here for the birth weights, what is the mean? The mean basically is you sum all the observations, divide by 10, you get 3.005 kg. Let me finish here by looking at the definition for the geometric mean. The geometric mean of n positive observations, x1, x2 up to xn, is the nth root of the product of xn, x2, x3 up to xn. So the nth root, now we know, mostly we know the square root, which is like the 2 if n is equal to 2. We normally refer to that as the square root. So the nth root, I would basically show you like this one. So it's the root of x1 times x2 times xn. So here we put n, big N, instead of just leaving. If we leave it like that, we know this one is the square root. But if we put anything here, like if we put 3, that's the cube root. So for example, if we had x1, x2 up to x3, we don't have any other numbers. If we take the product, so then we should be, the geometric mean is just the cube root. So we put a 3 here, that would be the cube root. But if we have 10, n is equal to 10, then the geometric mean here, we have to have the 10th root. So the 10th root of the product of all the observations that you've been given is the geometric mean. Okay, so although the geometric mean is very rarely used directly, the set of log of the observations is considered instead of the actual observed values, xi's. The mean of the logarithms of a set of numbers is equal to the logarithm of the geometric mean of the numbers. This is often applied to skew distributions, since the distribution after taking logarithms may be more symmetrical, and its mean, therefore, a good measure of the center. So, so far, we haven't yet tackled skew distributions. I think when we are going to look at the quantities like skewness and kurtosis, then you appreciate what a skew distribution looks like. And then at that time, then you would appreciate why taking the log of the observations would make sense before even just obtaining the mean directly, than obtaining the mean directly. So thus the geometric mean is often regarded as a better central measure of the arithmetic mean for a skew distribution. So when you have a skew distribution, it's better you use the geometric mean than using the arithmetic mean. And we are going to look at skewness for you to appreciate if a distribution is skewed or if it's not, if it's symmetric. So symmetric means that the distribution is not skewed. But at this moment, just maybe take that, but we will come to that at a later stage to see what a skewed distribution looks like. Okay, so thank you so much.